How to understand coding theory or error correcting codes, we need to cover some mathematical background, especially linear algebra. But linear algebra not over normal fields like real or complex, but over finite fields. So I'm going to give you brief introduction to finite fields. So before starting finite field, I'm going to ask what is a field. Okay. So first of all, I'll give you some very brief introduction of number system. I think this you might recall from your first day lecture in calculus. I might have given you a very brief 5 minute introduction of uh, number system. We have set of natural numbers, right? 1, 2, 3, 4, 5, 6, and then we have uh, set of integers because there were equations which we cannot solve in set of natural numbers, set of integers, then set of rational numbers. So here actually Q, R, and C special set of numbers because they are known as field. Field means a set of numbers where we can play with all four operations: addition, subtraction, multiplication, and division. So we can do all the four operations here. Addition, subtraction, multiplication, and division. So those sets are known as field. So we have Q, R, and C are field. But these are examples of infinite fields because number of elements in each of these sets is infinite. I'm going to give you an example of now, uh, finite field. Okay, finite field means a field with finite number of elements. So what is field? Field where we can do all the four operations: addition, subtraction, multiplication, division. I can just write it down for you. Fine. Field means I can do all the four options: addition, subtraction, multiplication, and division. Okay. So if you go to the finite field, I would like to ask: is there any field with one number of element? So can I say that there is a field with one number of elements? So it is not possible because field we will have operation with respect to addition and multiplication. So with respect to addition, there should be additive identity, that is 0, and with respect to multiplication there should be multiplicative identity, that is 1. Now because 0 and 1 are two very important things, they should be present in all the fields. So field with one number of element is not possible. Okay. So what I am going to do now, I am going to construct integer modulo 2 consisting of 0, 1 with operation plus 2 and dot 2. So this is really interesting. Let me see what is this Z2. So Z2 is, as I said, and I am going to start with making table plus 2, 0, 1, 0, 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 2. 2 modulo 2 is 0. So 1 plus 1 is 0. I go and start making another table with respect to multiplication modulo 2. Again 0, 1, 0, 1. 0 into 0 is 0. 0 into 1 is 0. 1 into 0 is 0. And 1 into 1 is 1. Now, if you observe these two tables, this is with respect to addition modulo 2 and multiplication modulo 2. We just want to check whether this is really a field or not. So, I mean, it is enough if we check that. Of course, it is closed. You can see that if we start with an element 0 and 1 and do the operation, we are again getting 0 or 1 only. So that is fine. Whether every element has an inverse. If we actually look at 0 here, you know, and so that means 0 is inverse of itself. So that means 0 plus 0 is equal to 0, right? 0 is self-inverting. And what about second 0 if I look at? So that means 1 plus 1 is equal to 0. So 1 is inverse of itself with respect to addition. Okay. Uh, Now, if you look at with respect to multiplication, we have 1 here as a multiplicative entity. So 1 into 1 is equal to 1. So 1 is inverse. Of course, we are not looking for inverse of 0 because 0 we cannot divide, we don't divide from 0. So this is nothing but known as binary field because it has only two elements. Okay. Now, if we have got an example of a field with two number of elements, 0 and 1. This is binary field, very fundamental field, smallest field, and that is the reason our computer is based on packets, binary packets. Binary field is essentially at the heart of our computer packet. Now, if I move a little bit further, now I want to construct a field with three number of elements. So I am looking at construction Z3, integer modulo 3, elements are 0, 1, 2, operations are plus 3, and multiplication of 3. Plus 3 means again we have 0, 1, 2, 0, 1, 2. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 1 plus 0 is 1, 1 plus 1 is 2, and 1 plus 2 is 3. 3 modulo 3 is 0, 2 plus 0 is 2, 2 plus 1 is 3, and 3 modulo 3 is 0. 2 plus 2 is 4, modulo 3 it is 1. Similarly, with respect to multiplication modulo 3, I am going to make a table 0, 1, 2, 0, 1, 2. So 0 into 0 is 0, 0 into 1 is 0, 0 into 2 is 0, 1 into 0 is 0, 1 into 1 is 1, 1 into 2 is 2, 2 into 0 is 0, 2 into 1 is 2, and 2 into 2 is 4. 4 modulo 3 is 1. So again, I can check the additive identity here in this table. This shows that 0 plus 0 is 0, so 0 is self-inverting. Look at the second identity. That means 1 and 2 are inverses of each other. So I can write down 0 plus 0 is 0, 1 plus 2 is 0. So 2 and 1 are inverses of each other. And if I look at the third 0, that means same thing as 2 plus 1 is equal to 0, right? So 1 and 2 are inverses of each other with respect to addition. And 0 is self-invertive. So every element in Z3 has its additive inverse. Now, if you move to the multiplication table, we have two places where there is multiplicative identity 1. So we have 1 into 1 is 1, and 2 into 2 is 1. That means 1 is inverse of itself and 2 is inverse of itself with respect to multiplication. Any question at this point? Any question at this point?
No, sir.
Okay. So you are able to understand field with two number of elements and field with three number of elements, Kishan?
Yes.
Okay, fine. So let me go to the next. We need to insert language. So we talked about field with two number of elements and field with three number of elements. Now I am going to do and look at field with four number of elements, four case. So for four case, we have Z4. Z4 with elements 0, 1, 2, and 3 with addition modulo 4 and multiplication modulo 4. So let us make table 0, 1, 2, 3, 0, 1, 2, 3. This is with respect to addition modulo 4. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. What is 1 plus 3? 4. 1 plus 3 is 4. Modulo 4 it is 0. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4, which is 0. And 2 plus 3 is 5, which is 1. Then we have 3 plus 0 is 3. 3 plus 1 is 4, which is 0. 3 plus 2 is 5, which is 1. And 3 plus 3 is 6, modulo 4, which is 2. So this is the table with respect to addition. Let us make a multiplication with respect to, let us make a table for multiplication modulo 4. 0, 1, 2, 3, 0, 1, 2, 3. So 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 0. Sorry, I'm really sorry. I am trying to add. I should multiply. I'm sorry. I think I need to go back. Go back. Yeah. So 0 into 1 is 0. 0 into 2 is 0. 0 into 3 is 0. 1 into 0 is 0. 1, 2, 3. 2 into 0 is 0. 2 into 1 is 2. 2 into 2 is 4. 4 modulo 4 is 0. And 2 into 3 is 2. 2 into 3 is 6. Modulo 4, which is 2. 0, 3. 3 into 2 is 6. Modulo 4, this is 2. And 3 into 3 is 9. Modulo 4 is 1. Now, if you look at with respect to addition, 0 is here. So 0 is self-invertive. Look at another 0 here in the table. So 1 plus 3 is 0. 2 plus 2 is 0. And so what does this say? 0 plus 0 is 0. 1 plus 3 is 0. So 1 and 3 are inverse of each other. 0 is invertive. But what about 2? You know, 2 plus 2 is 0. So 2 is self-invertive here, right? With respect to addition, there is no problem. Now, if we go and try to look at the multiplicative identity here in the table, 1, and there are only two ones here. So that says that 1 into 1 is 1. 3 into 3 is 1. But if you look at 2, 2 into 2 is 0. This is going to create a problem. Why? Because We have 1 into 1 is 1. Inverse of 1 is 1 itself. Inverse of 3 is 3 itself. But there is no inverse of 2. So this is not a field. In field, every non-zero element should have an inverse. So that means with respect to 4, we are not able to get a field. So we need to construct a field with 4 number of elements that I will tell you later. But from here, we can go a little bit further and try n is equal to 5 case. So let us take n is equal to 5 case. So Z5, is it a field? 0, 1, 2, 3, 4. And with respect to addition, modulo 5, there are two operations. Okay. So 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So 0 plus 0 is 0. 0 plus 1 is 1. 2, 3, 4. 1, 2, 3, 4. 1 is 5, which is 0. 2, 3, 4. 2 plus 3 is 5, which is 0. 2 plus 4 is 6, which is 1. 3, 4, 5 is 0. 3 plus 3 is 6. Modulo 5, which is 1 and 2. 4, 0. 4 plus 2 is 6. Modulo 5, 2 and 3. This is how we add with respect to addition. We can make a similar table for multiplication. Zero, 1, 2, 3, 4. 0, 1, 2, 3, 4. So 0, 0, 0, 0, 0, 1, 2, 3, 4. 0, 2, 4. 2 into 3 is 6. Modulo 5, which is 1. And then 2 into 4 is 8. Modulo 5, it is 3. 0, 3. 3 into 2 is 6. 6 is 1. And 3 into 3 is 9. Modulo 5 is 4. And 3 into 4 is 12. 12 modulo 5 is what? 5 to the 10. So it is 2. 0, 4. 4 into 2 is 8. Modulo 5, this is 3. Okay. 4 into 3 is 12, which is 2. 4 into 4 is 16. 5 3s are 15, so this is 1. Now if you look at the table 0. I just locate the zeros in the table. Another 0 here, another 0 here, and another 0 here. This says that 0 plus 0 is 0, so 0 is self-inverting. 1 plus 4 is equal to 0, so 1 and 4 are inverse of each other, and 2 plus 3 are inverses of each other, right? So every element 0, 1, 2, 3, 4 have inverses with respect to addition. Now here I should locate the multiplicative identity. 1, 1, okay, 1 here and 1 here. So now 1 into 1 is 1. 1 into 1 is 1. 2 into 3 is 1. And is 1. So inverse of 1 is 1. Inverse of 2 is 3. Inverse of 3 is 2. Inverse of 4 is 4. Okay. Now interesting thing that I'm going to ask you here. What is 1 by 2 here? Please unmute your mic and answer me this question. What is 1 by 2? Yes, Kishan? Yeah.
3.
1 by 2 is
3.
correct. So you see, it is not 0.5, it is 3,
Yes.
right? So this is something really interesting. 1 by 2 is 3, because 2 into 3 is 6, modulo 5, which is 1, right? So there are different things in the finite field, right? So now I am going to ask questions like, so we have seen for n is equal to 2, there is a field, right? N is equal to 3, there is a field. N is equal to 4, there is no field, right? We are not able to construct. But n is equal to 5, there is a field. What about n is equal to 6? Will there be a field? N is equal to 6. Yes, Kishan, can you answer? N is equal to 3. Sorry, n is equal to 6. Will there be a field? N is equal to 6. You can see that whenever n is prime number, there is a field. 2, there is a field, yes. 3, there is a field, yes. 4, there is no field. I mean, we are not able to construct by this method. 5, yes, we are able to construct a field. 6, again, we will not be able to construct a field, because you see, 2 into 3 will be 0. 2 into 3 will be 0. 2 into 3 is 6, modulo 6 will be 0. So there is no inverse of 2 and 3 there. Okay, just like that in Z4, 2 into 2 is equal to 0. There is no inverse for 2. So it is not a field. So Z6 is not a field. Z7, whether Z7 is a field? Yes, you can construct, because 7 is a prime number. Then one can ask, what about 8? Z8 is a field? No, Z8 is not a field. Okay, again, because 2 into 4 is equal to 0. Neither 2 is 0 nor 4 is 0. Field has very important property that if the product of two numbers is equal to 0, then one of them has to be 0. If A into B is equal to 0, then either A is 0 or B is 0. Okay, so Z6, it is not a case. Z8, it is not the case. Z9, we can ask Z9, is it a field? So no, it is not a field. Right. So like that, whenever n is a prime number, so we have this result actually, which I can mention to you. One minute. Gn is a field if and only if n is a prime number. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. So 2, yes, there is a field. 3, there is a field. 4, there is no field. 5, there is a field. 6, there is no field. 7, there is a field. 8, there is no field. 9, there is no field. 10, there is no field. 11, there is a field. 12, there is no field, right? So whenever there is a n is a prime number, we will be able to construct a field. Okay. So now, so this method is able to construct a field with 2 number of elements, with 3 number of elements. But what about the field with 4 number of elements? We still stuck. We don't know what to do. So let us try to focus the case n is equal to 4. We know that Z4 is not a field. So how to construct a field? How to construct a field with 4 number of elements? This is a very important question, and I'm going to show you. It's really beautiful construction. So first, what I'm going to do here. I will show you how we constructed complex numbers from reals. You see, we have field of real numbers, right? And what we did, we looked at a equation x square plus 1 is equal to 0, which has no root on the reals, and we constructed field of complex numbers by taking a root here. I is the root of this equation, imaginary number, and attach it to, so c is nothing but r attached with I. In other words, it is a plus ib form, such that a and b are reals, and I square plus 1 is equal to 0. I is the root of this equation. Okay. So this is how we constructed real complex field of complex numbers from reals. We are going to do the same analogy here, and for that we focus on Z2 as our binary field. From Z2 we will construct, Z2 is our binary field with 2 number of elements. We just saw Z2, right? From Z2 we are going to construct field with 4 number of elements. I am denoting a notation GF4. It is known as Galois field with 4 number of elements. So how do we do this? So in order to do this, we require a equation here which has no root over binary. For example, if you see here, x squared plus 1 has no root over reals, right? We cannot solve it over the reals. Then we attach, so that means the root will be outside the real line. So if I call the root to be I attach it to R, and we get a plus ib form. That means field with complex numbers. So same thing we are going to here now. So now if I look at degree 2 equations now, what are the equations? So let me write down all the equations. Ax square plus bx plus c is equal to 0. A is not equal to 0, and a, b, c belongs to Z2. So now I need to ask you, how do we solve this? Do you think that the Shridharacharya formula that we know to solve the quadratic equation, can we use it here? You can unmute your mic and tell me. Yes, Kishan, you want to say something?
Sir, we can make the equation like under root of uh, uh, first we change the constants and try to make the equation in the form of under root ax plus something whole square, and uh, the another part is the constant, so we can make the equation and both sides we apply the square root. We
No,
can
but square root, actually this is over finite field, so things are a little bit different. This is not the usual sense. I'll show you what I'm going to do here. First of all, since a is not equal to 0, so what are the other choice for a? 1. Because all ABC is either 0 or 1, right? They belong to Z2. They're either 0 or 1. So our equation is left with x square plus bx plus c is equal to 0, right? Because a is not equal to 0, so a has to be 1, right? So equation is this. Now, what does this mean? We have x square plus bx plus c is equal to 0. So one equation will be, so b is in Z2 and c is in Z2. So two choice for b and two choice for c. So total number of choices are 4. So there are 4 equations possible. X square plus, I can take b is equal to 1, say x square plus x is equal to 0, x square is equal to 0, and another equation will be x square plus x plus 1 is equal to 0. And what is another one? X square one equal to 0, right? So you can see that we are left with only 4 equations. Now, first condition that we need to check for each of these 4 equations, are there any roots in the Z2? Okay. So if we focus on first equation, first of all, let us focus on this equation. So x square is equal to 0. We know that x equal to 0 is a root here in the ground field. So this equation is not going to work. Okay, because this has root in Z2. What about this equation? X square plus x plus 0. Here also x equal to 0 is a root, right? This is also not going to work. What about this equation? X square plus 1 is equal to 0. We know that x is equal to 1 is a solution here, right? If we put x equal to 1, 1 plus 1 is 0. So this is also not going to work. Now if we look at x square plus x plus 1, if I put x is equal to 0, we will get 0 plus 0 plus 1. So x equal to 0 is not a root. So x equal to 0, not a root. What about x equal to 1? If I put x equal to 1, 1 plus 1 plus 1 is 3. Modulo 2, it is 1. So not a root. Since ground field has only 2 elements, I check both the 2 elements are not root. So this is our equation that we should look at it. In analogy, here with the complex from real to complex, we use this equation x square plus 1 is equal to 0. Here in this case, we got a equation x square plus x plus 1 is equal to 0. Okay. So this seems to be interesting. So let us try to use this equation. So that means we found the equation which has no root over Z2. Now I need to attach a root here which is outside Z2. Just like that in the from real to complex, we took I to be the root. I just call that root I. So here we are going to do the similar thing. Let us do it. Okay. So we have got the equation x square, 1 minute, x square plus x plus 1 is equal to 0 has no root over Z2, right? Because Z2 has only 2 elements, 0 and 1, and this has no root. Suppose, remember, in x square plus 1 is equal to 0 from real to complex, I was the root. We have assumed I is the root of that equation, so I square plus 1 is equal to 0. So here we call, suppose omega is a root here, which is not in Z2, outside Z2. So I will call it as omega square plus omega plus 1 is equal to 0. Okay. And I construct GF4 as following. There it was a plus ib. I am considering a plus omega b such that a and b are in z2, right? And we have the equation omega square plus omega plus 1 is equal to 0. Any question at this point? Are you able to get it?
Yes.
So there we have a plus ib, where I square plus 1 is equal to 0. Here we have a plus omega b, where a and b are in z2 and omega square plus omega plus 1 is equal to 0. Exact analogy from real to complex. We are doing it here in a similar manner. Now, I can list the elements here. So A and B are having two choices, Z2. A is either 0 or 1, B is either 0 or 1. So what we are going to get? If you put both A and B are 0, so we get 0. If A is 1, B is 0, we'll get 1. If A is, 0, B is 1, we'll get omega. And fourth root will be 1 plus omega. Right? So we have got these four elements. Now see the interesting thing here. 1 plus omega, what is the value of 1 plus omega? From here, from this equation, omega squared is nothing but minus times omega plus 1, correct? Right? From here. Now, minus 1 is same thing as plus 1 because 1 plus 1 is 0. It's z2, modulo 2. So, this is nothing but omega plus 1. So, omega plus 1 is nothing but omega square. So, we have simplified. So, we have elements as 0, 1, omega square, where omega square plus omega plus 1 is equal to 0. That condition is always there. Right? So, let us make a table and see that whether we have constructed a field or not with respect to addition. Zero, 1, omega square. 0, 1, omega square. So 0 plus 0 is 0, 0 plus 1 is how much? 1 omega square. 1 plus 1 is 2. Modulo 2 it is 0. 1 plus omega is same thing as omega square. 1 plus omega square is what? Is omega, because 1 plus omega square is what? You can check that 1 plus omega square is equal to minus omega, which is same thing as omega. Okay. Omega plus 0 is omega. Omega plus 1. 1 plus omega is omega square. Omega plus omega is 2 omega, which is 0. Omega plus omega square is what? From here. So omega plus omega square is equal to minus 1, which is same thing as plus 1. From this equation, omega square plus omega plus 1 is equal to 0, right? We have got 1. Similarly, yes, us.
2 omega is how it is possible.
Yeah, please tell me. Can you repeat? I can't hear you. Yeah,
Omega plus omega, how it is possible.
because there is a two component there, right? 2 omega. Modulo 2 is 0. Anything with multiple of 2 or like 2, 4, 6. See, modulo 2 means what? And either it is 2 or any multiple of 2, it will be 0. Okay, so since it is 2 omega, so it is 0, modulo 2. Okay, actually it's a characteristic of the field. Okay, got it? So last line, omega square plus 0 is omega square plus 1 is omega square plus omega is 1, and omega square plus omega square is 2 omega square, which is 0. So I can check. We have zeros here. I can, circle the zeros, right? Similarly, I can make a table for multiplication. Multiplication 0, 1, omega, omega square, 0, 1, omega, omega square. So 0 into 0 is 0, 0, 0, 0, 0, 1, omega, omega square. Omega into 0 is 0. Omega into 1 is omega. Omega into omega is what? Omega square. Can you answer me what is omega cube? What is omega cube? I can compute it here for you. Omega cube will be nothing but omega square into omega, correct? But omega square is nothing but 1 plus omega into omega, which is same thing as omega plus omega square. But since omega square plus omega plus 1 is equal to 0, this is nothing but 1. Okay? So omega cube is equal to 1. So this is 1. Omega square into 0 is 0. This is omega square. Omega square into omega is omega cube, which is 1. Omega raised to power 4 is omega cube into omega. Omega cube is 1, so this you are left with 1. So I can circle here multiplicative ints. And now you can check that every element 0, 1, omega, omega square has additive inverse. 0 plus 0 is 0. 1 plus 1 is 0. Right? Then we have omega plus omega is 0 and omega square plus omega square is equal to 0. So every element 0, 1, omega, omega square has additive identity. We also have multiplicative identity for every element other than 0. 1 into 1 is 1. 1 into and omega into omega square is equal to 1. Right? So omega and omega into omega square is equal to 1. So omega and omega square are inverses of each other. Right? And 1 into 1 is 1. So I think first I would like to stop at this point and ask you a question. Any question, any doubt here? Any doubt? Now, actually, you may ask, have you heard of complex cube root of unity? You can unmute your mic and ask, and tell me, have you heard of complex cube root of unity? Omega, right?
Yes.
Omega cube is equal to 1 there also, right? Is there any confusion with that and this? The question is, are they same or are they different?
They should be different because in complex cube root of unity, we have the equation 1 plus omega square equal to 0. And
That we
in
have
that,
here also, but that we have here also, right?
but here what we what we can derive also is that minus 1 plus omega square is equal to 0.
Yeah. So
And also,
basically this omega square plus omega plus 1 is equal to 0. We cannot solve it here, we cannot solve this equation because this is a finite field. So there, I can apply Shidhar formula and solve the value of omega in terms of this minus 1 plus minus. There is something in the form of root of 5 and so on, right? If you remember the value. So you are correct. Both of them are different actually, right? This is looks like it's a complex cube root of unity because it's saying, the equation is same and omega cube is also is equal to 1 here. There also it is 1, but they are different. You are right. They are different. Okay, because this is finite field. Things are a little bit different here. Okay, so if we go back and look at, so n is equal to 2, there is a field. N is equal to 3, there is a field. N is equal to 4, we constructed a field just now. 5, there is a field. What about 6? Can we construct a field with 6 number of elements with a similar construction? So the answer is no. At 6 there is no field. So essentially when there is a field, when there is no field, it depends on n. So actually if n is prime, there is certainly a field, or if n is a prime power. So like here it is 2 square, so there is a field. 3 square, 9, there will be a field. Okay? Anything which is prime power, there will be field. 12, there will be no field. You cannot construct a field with 12 number of elements. So this is the very basic understanding that there is a field with certain number of elements. So I can actually say so.
Is it 8 is a field?
Yes, 8 will be field. So the question is, how do we construct 8 field with 8 number of elements? So remember, I think I should mention another thing. Here, these two here, you see, these two here, these two here has something really interesting. Construct so field with here we wanted to construct this is 2 square. 2 should match. If I'm constructing field with 4 number of elements which is 2 square, so that means I am going to look at an equation of degree 2. Okay. In case of GF8 means field with 8 number of elements. So let us write down with GF8. It is GF means Galois field because Évariste Galois invented them. So I need to look at the equation of degree 3 now. So means equation will be ax cube plus bx square plus cx plus d is equal to 0, where a is not equal to 0 and a, b, c, d belongs to d2. Okay, so this is the equation we need to look at it. Okay, from this so maybe how many equations will be possible? As you know that a is not equal to 0, so the only possibility is, yeah, there will be 8 equations. So it will have be x cube plus bx square plus cx plus d is equal to 0. So now the question is, what are those 8 equations? Can we write down all of them one by one? X cube is equal to 0, right? When all BC D is equal to 0, then x cube plus x square is equal to 0, x cube plus x square plus x is equal to 0, then x cube plus 1 is equal to 0. Then what are the other equations? X cube plus x square plus 1 is equal to 0, right? X cube plus x plus 1 is equal to 0. Two more equations are left, right? What are those? Yeah, you can answer. You can help me. Yeah.
X cube plus x is equal to 0.
X cube plus
X is equal to 0.
x equal to 0. Good. And one more.
X cube plus x square plus x plus 1 is equal to 0.
X cube plus x square plus x plus 1 is equal to 0. Very good. So now we have 8 equations. Now the question is, which of these equations are useful for us for constructing the field? So if you look at, x cube is equal to 0. So this is not useful because x equal to 0 is a root here, right? Right? This equation is also not useful because x equal to 0 is a root. This equation is also not useful because x equal to 0 is a root. This equation is also not useful because x equal to 0 is a root. What about this equation? Can I say this equation is useful? No, because x equal to 1 is a root here. 1 plus 1 is equal to 0. Last equation is also not useful because x equal to 1 is a root. 1 plus 1 plus 1 plus 1 is equal to 0. So we are left with two equations, right? X cube plus x square plus 1 is equal to 0, and x cube plus x square plus x plus 1 is equal to 0. Which equation we should take now? Right? So the question is, which equation should we take now? I think we can take either this equation or that equation. It doesn't matter. Both of them will give us a field with 8 number of elements. So I suggest, you know, at home, as an assignment, try to construct a field with 8 number of elements with a similar method. So now taking omega as a root of x cube plus x plus 1, so omega cube plus omega plus 1 is equal to 0. And then this time you need to construct the field like this. GF8 is A plus B omega plus C omega square, such that A, B, C belongs to Z2, and one equation will be omega cube plus omega plus 1 is equal to 0. This is one construction. Okay. Second construction could be, we take GF8 as A plus B omega plus C omega square, such that A, B, C belongs to Z2. Okay. And omega cube plus omega square plus 1 is equal to 0. Got it? So there are two ways to construct the field with 8 number of elements. Either we use this equation, omega cube plus omega plus 1 is equal to 0, or we use the another equation, omega square plus 1 is equal to 0. In either way, we will be able to construct a field with 8 number of elements. So I think I would like to suggest that now at home you can try to construct this field with 8 number of elements in both the ways. So what you need to do, you need to make the table with respect to addition and table with respect to multiplication. So you can show it to me. You can do it by either handwriting or whatever, and show. I don't know whether if you can show it to me or not, but maybe you can share your file here and show me. So I think you should try at least home before proceeding further. I invite you to construct both of these fields, the table for addition and table for multiplication. And also I think if you go here, so you see field with 4 number of elements. I have constructed a field with 8. I have given you a hint how to construct. Also with respect to 9, what will happen with respect to 9? 9 will be 3 square. It's a prime power. So there will be a field with p square. So I think I can write it down here. Galois field with q number of elements. Field with q number of elements exist if and only if q is a prime power. A prime power for m. So that means I think I should tell you something like this. We have GF2 here, which is our Z2. From Z2 we constructed GF4, 4 number of elements. From here we can construct GF8. Now actually GF8 can be constructed from GF2 the way which I have shown to you. It can also be constructed from GF4 directly by taking a degree 2 polynomial there. Okay, so both ways are possible, but I think I would suggest you to follow this path from GF2 to GF8, to construct GF8. So basically there is a tower of fields, so we have GF2 here, Then we have GF2 square here. We have GF2 cube here. And finally, we have some GF2 raised to power m. Okay, for some m. This is known as tower of finite field. Okay, so similarly, we will have something for GF. So now actually, if you want to construct field with 9 number of elements, so you should say that we look at GF3. The base field is Z3 rather than Z2, and from where we construct GF3 square, which is 9, and like that we proceed. I think I will stop at this point, and if you have any questions, please ask me. I hope you understood everything, but if you have any question, please ask me so that we can close the class today. Any question? Yes, Kishan. Who are the other people? I mean, I don't know their name. I don't know whether. Yeah, Kishan, you ask any question here, please. Yeah. Any question? No?
Hello, sir.
Hello. What's your name?
Dilip.
Dilip. Okay. Hi, Dilip. So, any question? You understood everything?
Yes, for the we take equation x square plus bx plus y, we are taking that particular equation which is not root x equal to 0 and x equal to 1.
Yeah. So basically, we have to check the equation if there is no root in the ground field. So, we have an analogy with, for example, once we wanted to construct complex numbers field from real numbers, we have we have done the same thing. X square plus 1 has no root in the ground field. So we extended the field, from real to complex in the same manner. So we checked x square plus 1 has no root in the ground field. So here also we are looking at for each of these equations, they should have no root in the ground field. And then we are attaching the root to extend the field. Okay, so that is the common way of extending the field. Okay, so I'm going to post these notes as well as I think our lecture also I will post. I need to see how big is the lecture, but I hope it is not quite big. But yeah, so that you have access to them. And I wanted to also create a WhatsApp group so that I can communicate with you directly, without this email, because email takes a lot of time sometimes. So if you can create a group among yourself, that will be really good, and include me. I have written my number there in the email, and so that we can communicate efficiently. Okay. Thank you. So I think I'll stop at this point. If you have any question, otherwise, you please send me an email also, and I'll be happy to answer you. Okay. So what we covered today was modular arithmetic and the beginning of finite field with uh, 4 number of elements, uh, you know, 8 number of elements, and so on. And we'll come back to this topic again in the next week. Okay, thank you.